All right, we did not do this one, but how hard could gauging the size of an atom be, right? So the thing about size is if you're talking about the main group elements, it gets bigger as you go down the group, and that makes sense. One of the things I must have on a slide coming up is if you think about what an atom is, it has a nucleus and electrons around the nucleus. Remember that atoms are mostly empty space, which is kind of creepy. And so the thing that makes the size of an atom is the electron cloud, okay? So when you go down the same group, like if you pick on, you know, lithium, sodium, potassium, rubidium, cesium, I mean, you put on a crap load of electrons going down the group, okay? And that electrons are basically what makes the size of an atom. So maybe not quite as intuitive is if you're talking about elements that are in the same period. This top one is counterintuitive, and I'm going to have to try to explain I'm going to explain it using something called effective nuclear charge. But this one is less intuitive. I'll just put less intuitive. Okay. Why, if you're in and the reason it's less intuitive is we know if we go from left to right, we're getting more electrons. So why does it get smaller from left to right? Because that's what it does. So like I said, those arrows work pretty good for the group A elements, which again, you got to kind of know your way around the periodic table. We have the 1A, 2A, and then we have the 3A through 8A, the S block and the P block. So let's see if these work. They might. I guess I need some sound too. This one? So this kind of is talking you through how do we know the size of an atom? Well, if we pick on chlorine, the cool thing about chlorine is, remember, chlorine is one of those 7 elements that buddies up, so it's always Cl2.
The radius of a single chlorine atom is defined as 100 picometers, which is half the distance between the centers of the atoms in a Cl2 molecule.
Remember, it's one of those diatomic elements, so it's H2, Cl2, O2, thus, okay. So PM stands for, the P here is pico, so picometers. Okay, so that's one way to gauge estimate the radius of one of those, then would be 100 picometers. I love the word pico. I just think that's so funny. So again, PM stands for picometers. So you see kind of an assortment of atomic radii. I like that term, atomic radii too, where you start from the nucleus and you go basically out to the edge of the electron cloud, which is kind of a strange thing to kind of guess, the electron cloud. But up here we have a couple forms of sodium. Sodium, actually 2 sodium atoms covalently bonded. Here's sodium atoms as they kind of hang out in solid sodium. Notice there's a slight difference in their atomic radii. Down here, this last one, actually we're going to spend some time in, let's see, part 5. Part 5, we're going to pick up with talking about the sizes of ions. And actually, when chlorine picks up an electron to form this chloride ion over here, okay, check out its size. Okay, you're talking, well anyway, let's pick on sodium. When sodium loses an electron to form a sodium +1 cation, check out its size. It's 99 picometers instead of the atomic radii was 186 to 157. So we're going to see cations get smaller and anions get larger. So these are your 8 groups of main group elements going from left to right. Oops, I guess the one that's missing, we're missing the rare gases, 8A. But hopefully you can see the trends we talked about. You know, the first trend is pretty easy. You know, we increase as you go down. Okay, maybe not so intuitive is it increases. You can see right here, remember PM stands for picometers. Actually, these are all in picometers. But atomic size increases as you go from right back to left again. But this is usually where some students will say, no, there's an exception. Oops. There's an exception here. There are a few exceptions, but in general, we are increasing as you go that way. There's an exception here. Okay, get your critical mind going. But in general, it increases. We'll talk about why that increases in terms of something called Z-star, or effective nuclear charge, coming up. So what these are, you might recognize them as periods. So from lithium to fluorine, that is period number 2. Okay, from sodium to chlorine, period number 3, 4, 5, okay, 6. Yes. So what you're looking at is within the same period, how the size does in general as you go from lithium, which is atomic number 3, to fluorine, which is atomic number 9. Okay, notice that the size gets smaller. Size gets smaller. There's a little bit of a bump, but the size gets smaller. Those are going across the period. Okay. So like I said, you know, this trend is pretty obvious. Okay. This trend of increasing from right back to left again, is not so obvious. So we're going to dive in and take a little bit of look at why are sizes of atoms the way they are. And in order to understand the size of an atom, we need to take a look at kind of the dynamics within an atom, what's happening. So, of course, ever since, I don't know which scientist it was, but I want to say Rutherford but we know that we have protons in the center of an atom and electrons out here making the volume. So it's kind of a battle between, like this says, attractive and repulsive forces. The whole positive and negative, that's attraction, okay? But within this cloud out here, negative and negative, that's repulsion, okay? So negative makes it larger, okay? As that repulsion increases, if there's an attraction here, okay, the size will actually decrease. Okay. So if the attraction forces, that would be between the positively charged nucleus and the electrons. Okay, if that increases, I'll go ahead and kind of show like that, it's actually going to make a smaller structure. If we go down here, we have a nucleus in here, and we'll put a couple electrons out here. Electrons are going to repel each other. If this increases, it's going to make your atom larger. Okay, so here's the deal then. I get my left and rights mixed up. I have to focus. Okay, as you go from left to right, the size decreases. And we know that there must be then a decrease because, is that left or right? Yeah. They're getting smaller because the attractive forces are getting larger. Attractive forces are getting smaller because attractive forces are getting greater. Okay. That increases as you go from left to right. So there's a lot of trends in the periodic table where we kind of throw out the group B elements. Remember, the group B elements have your transition elements and your intertransition elements. The intertransition elements are the lanthanide and the actinide series. Okay, so we see kind of a trend, but not an absolute trend. Actually, I would argue you don't see an absolute trend in the other one either, or in the main group elements. But I put together a little, because we're almost done, almost to the assignment slide. I put together like a little separate one slide to talk about effective nuclear charge. But effective nuclear charge basically says that, like the slide says, your non-valence electrons, so your inner electrons, actually shield what your valence electrons feel when it comes to the protons in the center. Okay, so Let me go ahead and take you to this one. I'm going to put this one on my refrigerator. All right. So effective nuclear charge. It's Z star. So Z star describes this attractive force between the valence electrons, the outermost electrons, okay, and the protons in the nucleus. And actually, it's a little subtraction that can be calculated. And I'll go ahead and post this slide too, like I do I'll post this, but you can take notes too. So it's a quick and dirty little subtraction. So basically, for your atom of interest that you're trying to calculate the effective nuclear charge, the effect on your valence electrons, what you do is you take the number of protons in the nucleus, and from that you subtract those non-valence electrons because they actually are shielding your valence electrons from your protons in the center of the atom. So I have a couple examples. I picked two atoms in the same period to try to show you why, as you go from left to right, because of the effective nuclear charge within the same period, the atoms get smaller because the effective nuclear charge increases. So the period I picked was the third period. So I picked on magnesium. So magnesium's atomic number 12. So it has a neutral magnesium atom has 12 electrons, and this is how the 12 electrons are configured. You know, 2 electrons in the 1s, and actually 8 electrons in the principal energy level, n is equal to 2. And then we peter out with 2 electrons in the 3s subshell. So we have 2 valence electrons, and we have, 10 non-valence electrons. So to calculate the effective nuclear charge, okay, we take 12 protons and we subtract 10 electrons. Okay, so the way I think of effective nuclear charge, and I know I've read this and reread it probably, basically those valence electrons, there's 2 valence electrons in the 3s subshell, they both feel independent a pull of +2. Okay, so each of the 2 valence electrons in the 3s subshell individually are drawn to the positively charged nucleus with an effective nuclear charge of +2. So in order for this to make sense, let's go across in the same period and let's pick on phosphorus. Okay, so it's in the same period. Phosphorus has its atomic number 15. So we need to find homes for 15 electrons. So there's 15 protons in its nucleus. And of course we have kind of this inner core. That should be, I can add this. I missed a 6 there, didn't I? So if you compare actually the non-valence electrons, it's got the same non-valence electrons as magnesium, which makes sense. Okay, then it's got 5 valence electrons, and they're found in 3s subshell and 3 valence electrons in the 3p subshell. So the effective nuclear charge for those, again, 5 valence electrons looks like this, where you take 15 protons, and from that you subtract the non-valence electrons, 10. Okay, so +5 is the effective nuclear charge. What does that mean? It means that those 5 valence electrons individually are now being drawn not with an effective attraction of +2, but with an effective attraction of +5. So honestly, in the same period, okay, those 5 valence electrons, even though the 5 is more than 2, and you're like, hey, it should be more fluffy, okay, they are drawn to the nucleus, okay, with a greater effective nuclear charge. So that's why going across the same period like that, they'll get smaller. We could have filled in the blank and, picked on an aluminum and silicon, been the same thing. Effective nuclear charge. So these are due then, and like I said, I did go ahead and make something called Part 3. So we're going to get to 3 assignment slides, and I'll probably, what I've been doing is making all of your assignments, like if you had multiple assignment slides like that, making it worth only one assignment, you know what I mean? But depending upon if it's in the best interest of the group, or I'll go either way, I can break this up and you guys can earn 3 homeworks, and if it's split, that's going to have a problem, or just 1 homework. Okay, whatever's best for the whole group. But I have to be consistent. So here's my hints for these. For number 9, and actually on your unit exam for this material, I'm going to give you just like you see here. I usually do, I think, anyway. Basically, I pick 2 atoms and I say which one's bigger. And so what I have up there are the arrows for increasing size. Okay, so for main group elements, size increases as you go down, okay? And, well, actually for all elements, but for the main group elements, size increases as you go from right back to left again. So if you run into this, I don't know about homework, but on a test, I would really take your periodic table and I would circle the elements in question. So for the next one, I'll kind of put everything up there. For 11, that's in blue, okay? So I as much tried to tell you why the sizes of atoms don't increase. Well, see what you can do with that one. My hint is in blue there. For 12, blue, purple, and green. And for 12, actually says that how come it's hard to actually sink your teeth into the size of an atom? And to me, it kind of goes into you have to get a fix on the distribution of electrons in what we call the electron cloud. I think that's a hard thing to do. I think there's a little bit of fuzzy area. So that's my hint for 12. The hint for 13 there is in orange. 13 has a couple parts to it. It says, which is the smallest atom in group 13? That corresponds, if you look at kind of the new convention versus the old convention, that corresponds to 3A. So that's starting with boron, aluminum, blah, blah, blah. Okay, which is the smallest atom in that group. Should be the top one, right? And then the second part says, gives you a list of 5 atoms, and it says, you list them. It says, which is the smallest it leaves, and it says, why is it the smallest? So this is another place where I would find these on the periodic table and circle. Most likely you're going to be able to use kind of the thing, size increases as you go down and increases from right back to left again. All right. So, on to end of part 5. So for my estimation, this is where we need to be. And actually, this is kind of exciting because I've never done back-to-back sizes of atoms and sizes of ions, but it makes sense. I think it will be a good thing. So the 2 types, and we're just talking about monoatomic ions. So basically an atom, a metal that has lost an electron or 2, and a nonmetal that's gained an electron or 2. Okay? So to make sure we're all on the same base. Earlier in this part, we talked about how metals form cations, okay, and nonmetals pick up electrons and form anions. So in a nutshell, and I bet this makes sense, I mean, if you're losing electrons, okay, you are going to be smaller. I can't spell, I think it should be 1O. And if you're gaining electrons, you're going to be larger. Bottom line. But I've got some pictures to kind of show you. So I think you'll be fine with it. So this slide might look familiar. When we talk about the size of a neutral atom, okay, we said that what the electrons are doing with regard to being attracted to the nucleus, what the electrons are doing with regard to being repulsed from one another, kind of makes the size of an atom. So we have the same thing going on with these ions. And I think this is another deja vu slide. Okay, so as the attractive forces increase, your atom or your ion is going to get smaller. If the repulsive forces increase, your atom and your ion is going to get larger. So kind of the gold ones there are the neutral atoms, and then the blue ones there, these are both metals, are the cations, okay? Where, for instance, sodium lost 1 electron, okay, and it got smaller, went from 186, we saw that earlier, didn't we, to 99 picometers, the radii. And magnesium also got smaller, from 160 picometers for the neutral atom to 72 picometers for the radius of the +2 cation. So we saw a little video today that basically said to get to the radius of a chlorine atom, we kind of take a Cl2 molecule, split it apart, and get to the radius of a chlorine atom. It's about 100 picometers. If you compare that to a chlorine atom that's picked up an electron, guess what? This is bigger. Okay, so the anions are always bigger than the neutral atom. So this is kind of a clever little slide. And again, it's consistent with what you guys did in lab and what we talked about. We said, here's the jag. Of course, that separates metals from nonmetals. So here you see the metals losing electrons and forming these cations. These are cute little blue things. And here you see the nonmetals picking up electrons and forming these humongous green anions. So it's all good. So let's consider, and we talked about isoelectronic. I can't remember when we did. Seems like it might have been Wednesday. But isoelectronic species, remember I like the word species, are just things that have the same electrons. In fact, the electrons are configured the same. So if you find oxygen and fluorine, actually you'll see that they want to pick up electrons to become like neon. So these guys will pick up electrons to become like neon, the rare gas configuration of neon, which is equal to 10 electrons. Okay, and these guys will lose electrons to get like neon, so they're in the period after it. Okay. So sodium loses its 1 valence electron, goes from 11 to 10. Magnesium loses 2 valence electrons, it goes from 12 to 10. So these are all isoelectronic with the rare gas neon. So if we were going to want to kind of organize them in terms of size, now this is, I know I spent some time talking about Z star, the effective nuclear charge. We don't even have to go that far. Basically, what we have, if we draw a little picture, is each one of these, this will work, each one of these has either lost electrons or gained electrons to get the same rare gas configuration, okay, of neon. So if you want to talk about these as the 8 valence electrons, okay, notice that these are the nuclei that those 8 electrons are going to be drawn to. So here in a minute, if I let the size of my arrow be an indication of the attraction of these 8 electrons, we're going to see that those 8 electrons are really attracted to for the magnesium +2, okay, less for the sodium +1. Okay, so again, if the length of my green arrow is an indication of the attractive forces. So here on the next slide, you're going to see that this is the smallest. Okay, and actually, this is the largest. So again, it may seem kind of strange because if you find magnesium on the periodic table, you go past neon, 2 past neon. You're like, dude, how could that be so small? Well, that's because magnesium +2 cation has lost 2 electrons. And now the electrons it has are being drawn into the 12 protons in its nucleus. This isn't an effective nuclear charge thing. This is just a, hey, that's how that works. And I didn't emphasize it, but If you think of poor oxygen, you know, with what? Must have 8 protons in its nucleus. Okay, it used to have 8 electrons, and now it picked up more electrons. So not only does it have less of a draw to its core, to its nucleus, but it's got all this repulsive forces going on with regard to those 10 electrons now. So yeah, it's going to be pretty big. So here are the absolute sizes of the radii of those species in picometers. Isoelectronic with neon. When you have problems coming up for homework, I really would kind of map out the different species. That's my advice to working these. So let's take a look at these 3 problems. And they are right here. Okay, so these are the 3 problems due on this assignment slide. So I circled H plus, H minus, like really? And HE. So my advice for 14 is to go ahead and when I say lay it out, I mean, it's up to you, but I would do something like, you know, list them each. Might go in that order, I don't know. And then I would list like the number of protons in the center and then the number of electrons. Okay, and then kind of draw some conclusion from that. I would anyway. Hopefully that will kind of make it clear to you. It's like, okay, those electrons are drawn to that center, or those electrons are repelling each other. So 15 in blue there, C problem 14. Okay, so now it's the neutral bromine atom, the lithium cation, the neutral selenium atom, and the chloride anion. Again, I would kind of list them. You know, to me, that's just kind of an easy way to kind of take a bird's eye view at it and think of the attractive forces and repulsive forces. And then the last one, actually, those are all, and I haven't checked this, but I think those are all isoelectronic with something. See, bromine looks like krypton. Bromine and selenium. And then the next period, let's see, the cations are rubidium, strontium. Yeah, those are all isoelectronic with, I love krypton, with that. Okay, so this is very similar to what we just did with things that were isoelectronic with neon. All right. There's my hints for that one. Okay. So, ionization energy. When something is, when a gas is ionized, basically electron or electrons have been removed. Okay, so ionization energy is kind of like when we've been talking about forming a cation. Okay, metals tend to kick off electrons. There's a certain amount of energy always you have to add for an electron to leave. That's ionization energy. And it's expressed, like the slide said, in energy, usually kilojoules per mole of electrons that are kicked off. So if it's always going to be positive because you have to put energy in order to kick off an electron. If your ionization energy is kind of small, then you're like, hey, dude, that electron wanted to go anyway. Okay? So low ionization energies mean, in my idea, that it wanted to form a cation anyway. And metals tend to have low ionization energies because they want to form cations. So actually, this is the same trend as electronegativity. We say electronegativity increases from left to right and also increases from bottom up. Again, just for the main group elements, ionization energy increases. It means you have to put more energy in to kick off an electron as you go from left to right across the same period. And the group, it increases as you go from bottom up. And it says there are some exceptions. So this is an excerpt from your textbook that says for these elements, that's the ionization energy you need. Actually, we're going to see that there are, to kick off the first electron. So can you guys see this little subscript 1 here? That's to kick off the first electron. We're going to see that once you kick off the first electron, you can go back for the second electron if you want, and that'll be look at subscript 2. Oops, did I skip slide? Okay. So again, these kind of breaks in these are actually groups, just like we saw before. So beginning with lithium, that is actually group 2, sodium group 3. So it almost looks periodic, doesn't it? And that would make sense. That's not right. One more time. Okay. So these are just kind of another visualization of increasing ionization energy as you each color is a different period. So as you go across the period, it gets harder and harder to kick off an electron. And again, there are kind of some exceptions in there. You see that with aluminum and gallium and kind of a little bit sulfur and selenium, kind of a step down. So these are actually how the electrons are configured around the first, must be 8 atoms. And so, they're not entirely. Oh, now I remember this slide. I must have deleted something, because doesn't that look wrong to you? Yeah, I'm not going to go fix all of these, but the 4 electrons around a neutral beryllium atom look like this. Okay, boron is 5, atomic number 5. So I hope you guys just kind of bear with me there. So ionization energy, we said increases. This is going across the group, so it increases how these are kind of described from the top down. So I mentioned the little subscript I, I1, I2, I3. So it is possible, and we know that sometimes you want to remove 2 electrons. So for instance, magnesium forms a +2 cation, so of course you're going to remove that second electron. And so there would be an ionization energy associated with that removal. Okay, but the way it goes for any given atom, as you remove subsequent electrons, it gets harder and harder. Oops, sorry. So put another way, this is kind of saying it gets more and more difficult. More difficult, because you can tell by difficult by the higher ionization energy to remove. I'm going to put later electrons. So yeah. And I have an example. I'm going to pick on magnesium and kind of show you what we say, what it looks like for the first ionization energy, the second ionization energy, and the third ionization energy. So if we pick on magnesium, okay, to kind of get our bearings, like we know magnesium's a 2A metal, so magnesium has 2 valence electrons. It's going to lose those 2 valence electrons that are right here, right? And we know it's going to form a +2 cation. But let's look at it stepwise. So the first ionization energy would look like this. I think there is sound to these. Of course.
Removing the second electron requires more energy, 1,451 kilojoules per mole.
Oh, I thought I skipped a slide. Go away. All right. Let's do this one first. So neutral magnesium atom, you zap it with energy. Why? Because this is energy of ionization. And you get back an electron has separated and you're left with a +1 cation, which I know looks kind of strange, but it's on its way to a +2 cation.
To remove the outermost electron from a magnesium atom requires 738 kilojoules of energy per mole.
Okay, so actually I'm going to show you a figure from your textbook, and you're going to need to use this for your homework, where that number exists. 738 kilojoules per mole is the first ionization energy of magnesium. And like you saw this one, okay, now if you kind of read it, you have a Mg +1. You're going to zap it again, and you're going to end up with 1 mole of electrons for every 1 mole of magnesium +1 you zapped. And also on the product side, you're going to have magnesium
Removing the
+2.
second electron requires more energy, 1,451 kilojoules per mole.
So if you were tasked with finding out how much energy was required to get, for instance, a neutral magnesium atom from Mg0 to Mg +2, you would add those two. Does that make sense? Stepwise. So on the table coming up, there's going to be a big line between the second ionization energy and the third ionization energy. It's like a jag.
To remove a third electron from magnesium requires much more energy, 7,733 kilojoules per mole.
You know, and what you saw is it went from already a complete octet with 2 electrons in the S, 2s, and 6 electrons in the 2p, went from that octet to this. And it's like, dude. Okay, so to kind of summarize what you saw on the 3 videos, this is what you saw. First ionization energy, second ionization energy, and the third ionization energy. And like I said, and I don't know if there's necessarily a test question, but the reason there's such a big difference between the second and third ionization energy is it had a complete octet right there. Goodness, tet. Okay. And there, it went to no octet underneath there. So this is the table from your textbook that you're going to want to refer to do at least one, if not a couple of your homeworks in this last assignment slide. So you see the magnesium that we just talked about, okay? Aluminum, the reason there's such a big difference between the third and the fourth ionization energy is because it wanted to stop at 3, okay? Sodium, big difference between the first and the second ionization energy because it wanted to stop with 1. So kind of in contrast to ionization energy, there is this important property of atoms called electron affinity. And it's kind of the yang to the yin of ionization energy. Ionization energy is removing electrons, and electron affinity is gaining electrons. So when we look at the periodic table and the JAG and kind of separate the nonmetals from the metals, we know that nonmetals want to gain electrons. So honestly, we're going to see that they have what we call kind of a high electron affinity. When I get to this subject, I always think of like if you have an affinity for chocolate, you want lots of chocolate. Yeah. Okay. So, but here's the deal. We're going to use delta H's of EA. Electron affinity is EA. And we're going to keep with the convention we've been talking about. If your change in enthalpy is negative, then actually energy is released. Okay? And actually, if energy is released, then on the other side of that process, adding electrons, the ion is like, so happy. So that's why it says a stable species is formed. But there are some electron affinities that require energy to add electrons onto something. Okay? And those delta H's of electron affinities will be positive. So you had to work to make it happen. And actually, it's kind of like what ionization energies are. You had to work to kick off electrons. In some cases, you got to work to add electrons too. So I need to kind of, it's hard when you have positive and negativeness, or I don't know if that's right. But it's going to seem a little contrary then to say the trend in increasing electron affinity actually becomes more negative as you go towards the nonmetals. It's more favorable to add electrons. They want to have electrons added to them. Nonmetals don't want to have electrons added to them. Actually, we're going to see it become more negative though. It's the more favored situation. So we kind of have the same trend as we had for ionization energy as we had for electronegativity. Okay, not for atomic size though, with regard to electron affinity. But again, when we say increasing electron affinity, we mean that it's probably becoming more negative. A more stable species is formed. Okay. So this slide is very similar to the slide on ionization energy. Ionization energy can be kind of measured or kind of thought as an ion or an atom's want to kick off electrons. And electron affinity then is a measure of an atom or ion's want to pick up electrons. Because electron affinity, we're measuring the energy required or released when you dump on electrons. So metals have low electron affinity. They don't like the chocolate. And nonmetals have high electron affinities. They love the chocolate. Dump on those electrons. So again, when we see negative delta H's of electron affinity, the more negative, the more energy released. That means they're very stable. Something is formed. Positive electron affinities mean the energy is required to dump on electrons. So, So we can kind of think of it in terms of, again, these are positive. The more positive it is, the more energy is required. The more negative it is, the more energy is released. All right. So this is a table that might be helpful on your homework, those two tables. These are, I guess we could have the first electron affinity, the second electron affinity, etc. But you'll only need these first electron affinities, where we're trying to basically take a neutral atom and dump a mole of an atom or that particular element and dump on a mole of electrons. And that's the amount of energy in kilojoules that you need per mole of electrons added. So again, the trend's a little, but you should be okay if you think of it as being the same trend as ionization energy. And again, I'm missing some electrons. Not sure why that is. But across the same, this is period 2. Going across the period, electron affinity increases as you get closer to the nonmetals.
When a gaseous atom accepts an electron to become an anion, the energy it releases is a measure of its electron affinity. For chlorine, this is minus 349.0 kilojoules per mole.
Very good. I like how she said anion. Okay. Okay, then we get to an assignment slide, and I'll take a look at these right quick. I have hints for these. I kind of grouped them in 21 through 24, and then 27 has its own slide, and I think 28 has its own slide. So, let's see. It's been a while since I had to, like, annotate homework. Where are you, 5B? Okay, so my hint for 21. 21 simply says, give some elements, strontium, cesium, sulfur, fluorine, and astatine. I get my AS's mixed up. Whatever AS is. Thank you, arsenic. Okay, find them on the periodic table, and hopefully you can use those trends. Okay, it increases from left to right ionization energy, and it increases up the group. For 22, my hint is, actually I put all of them up here. For 22, it's in green there. It says, is it ever such that the second electron to be removed takes less energy than the first electron to be removed? And in green, I said no. And then I said, basically, consider for that second removal of electrons, think of trying to take an electron away from a cation. Okay, it's already down one. You're going to take another one away from it? Okay. 23 is in purple up there. So some electron affinities. So we're switching gears from ionization energy to electron affinities. Some are positive, some are negative. And in purple I say that's because some can require energy and some can release energy when you dump on electrons. And then the second part of 23 says, why is it not the case with ionization energy? In red, I say it always takes energy to kick off an electron. So that should do it. I answered it for you. For 24, it's kind of a factor label problem. If you read it, basically it's describing the ionization of a neutral sodium atom. So you take neutral sodium, okay, you add energy to it, and the energy required for the first ionization actually is given in the problem. And it says, all right, what about how much energy is required to ionize 1.00 milligrams of sodium? So I would take that mass and convert it to moles using the molar mass, and then apply this energy per mole of sodium. Okay. The next one, let me go ahead and, how did this get so craziness? This must be the next one, I think. Do it this way. All right. So the next one says, is that the next one or is it 27? Did I miss one? Oh, I missed one. I missed the bromine one. So you're on your own with the bromine one. But this one basically says, for the overall process for making the ionic compound, basically, magnesium fluoride, kind of think of it in stepwise. Basically, you need to kick off 2 electrons from your magnesium atom. And you think of that stepwise, and actually there's an enthalpy associated with that you can get from that table. And then you need to consider adding electrons onto the fluorine atom, and you get that from that chart. But notice that that's in joules instead of kilojoules, and notice you need to multiply that by 2 because to make it work out. And then you are ready to go ahead, and this overall process with the starred equation actually can be summarized as these 3 enthalpy changes, as long as you make sure that you multiply this one by 2. And so you can come up with the enthalpy associated with that overall change. Okay? And I'll come up with something for bromine and put it up there. All right. Have a good weekend.